can see ground fault overvoltage with inverter-based distributed energy resources given by Dr. Aboutaleb Haddadi, who's a senior engineer scientist at EPRI, where he works on grid monitoring, protection, control, inverter-based resources. He's also chair of SIGRE working group C460, working on generic EMT models for inverter-based resources. And he holds a PhD from Polytechnique Montreal. So Aboutaleb, thank you very much for being part of this year's user conference. The floor is yours. I also invite all of the attendees to type their questions in Zoom. As soon as you have a question, type it in the Zoom, and then we'll answer at the end. Thank you very much.
Thank you, Mihailo, and thanks to EMTP for this opportunity to present. So let me go ahead and start moving my slides. Okay, so basically, in this presentation, I will give you an overview of the recent work that we did for a North American utility study on ground fault overvoltage with inverter-based distributed energy resources. And I will first try to give an overview of the case study that we performed, and then we'll talk about key findings and conclusions. And feel free to ask me any questions, or even during the presentation if you want to go ahead and do it. So without further ado, quick background, basically ground fault overvoltage with DERs. The industry trend is integration of more and more distributed energy resources, DERs, in distribution networks, solar PVs, battery energy storage units, and this leads to formation of active distribution networks. And the challenge that comes with this is the increased possibility of large DER islands. Essentially, when there's a fault upstream and the main breaker of the distribution feeder opens, a chunk of the distribution systems become islanded, and it continues to be energized by DERs. So that's what we mean by an island. And this increases the risk and possibility of a ground fault overvoltage and leads to GFOV concerns. So what is a GFOV? Essentially, it's an overvoltage condition caused by a line to ground fault, and in certain substation configurations and transformer winding connections, this leads to an increase of voltage on healthy phases, and therefore the equipments that are subjected to this overvoltage, for example, the surge arresters or breakers, the open breaker, basically they could be damaged. And it is necessary to study this and make sure that the equipments are rated accordingly. And so what is the challenge, the main challenge with GFOV? It's basically that with increased levels of DERs, the GFOV concern becomes more significant. Basically, the overvoltage is expected to increase, and that poses, it's essentially a barrier to large-scale DER deployment. It either poses low hosting capacity caps on distribution networks. For example, you cannot go beyond a certain percentage of your load. You cannot have, let's say, for example, more than 67% DERs, or it increases cost of DER projects. If you want to go beyond that cap, you need to install mitigation options, and those mitigation options could be costly. So it increases the cost of DER projects and could render them unfeasible. So essentially, there is a need in the industry for development of first to understand if there is such an issue, if there is a GFOV issue, there's a need to model and analyze basically the networks and to determine when high DER integration presents a GFO concern, and secondly, to develop low-cost and GFOV detection and mitigation options. So this could range from transformer protection and other solutions, for example, arrestor sensing that we'll briefly talk about. So essentially, the GFOV must be avoided. And here's a closer look at what exactly it is that we're talking about, ground fault over voltage. So consider we have a distribution feeder, let's say 12.47 kV distribution feeder. It contains PV and other types of generators and also loads. And this feeder is energized, is supplied from a substation. And the substation is connected to a subtransmission network. And the subtransmission network is connected to the utility bulk source. So there is a main feeder breaker to protect the subtransmission network against faults. And essentially, when there's a fault happening on the subtransmission network, this main feeder breaker opens, so the entire subtransmission network becomes islanded. Now, if there are generators in the distribution feeders, and if the substation remains connected to the fault, this is an active island. Basically, the generators continue to energize the fault, and in that case, if the substation transformer has a primary winding that is ungrounded, it's either could be a delta winding or ungrounded Y, then this ground fault leads to an increased voltage on healthy phases, unfaulted phases. And this voltage could be as high as 1.73 per unit, and it lasts until the DERs cease to energize the island, which could be up to 2 seconds. So during that 2 seconds, the equipment, the transmission equipment, for example, the arresters, they could be exposed to up to 1.73 per unit phase to ground over voltage. Also, the main feeder breaker, on the one side, it sees the block utility voltage. On the other side, it sees the island voltage. And if there is frequency shift in the island, this breaker could see potentially up to 2.73 per unit phase to ground over voltage. So these equipment need to be rated accordingly, and basically we need to study this level of overvoltage and basically to be able to analyze the risk. And so this is essentially what we talk about here. So in conclusion, the GFOV issue may exist. There are two conditions that need to be met in order for the GFOV risk to exist. First is that the distribution circuit should remain connected to the transmission line fault after the opening of the main feeder breaker. And the second condition is that the substation transformer has an ungrounded primary winding. So essentially, there is no grounding source to the subtransmission system from the distribution system. So there are some substation configurations where the connection to the fault does not exist after opening of this breaker. For example, if you have another breaker on this side or on this side of the substation, then the distribution circuit is isolated, so there is no risk. Also, if the primary side is grounded, there is a grounding source to the subtransmission, so there is no issue here. So basically, our case study concerns specifically this configuration where you have an ungrounded transformer and substation configuration where the distribution system remains connected to the fault. So just a quick background and theory on what happens in traditional systems with synchronous generators. Let's assume we have essentially a synchronous generator supplying the fault or energizing the fault. A synchronous generator behaves like a voltage source. So assume that we have a three-phase voltage source connected to a three-phase load, and the neutral point of the voltage source is not grounded. And assuming everything to be perfectly balanced, under normal operating condition, the neutral point voltage is 0. So the voltage across neutral to ground is 0. Now, assume that a fault happens on phase B, so the voltage on phase B drops to 0. Because this is a voltage source, the voltage on phase BN the voltage of BN is kept constant. So the neutral voltage here shifts. Essentially, it becomes equal to VBN. And because of the shifted neutral voltage, the voltage of phase A and C, the unfaulted phases increase because now they are the voltage of pre-fault of phase A plus the new neutral voltage. So theoretically, they could increase up to square root 3 of the pre-fault value. And this could also be illustrated visually here. Before the fault, you have a set of balanced phasors. And when the fault happens, the neutral point shifts towards the faulted phase, and therefore the phase to ground voltage on unfaulted phases increased to 1.73. This is with traditional system. The mechanism for overvoltage is shifted neutral, and the mitigation is effective grounding. Basically, it's a way of designing a power system to limit the amount of neutral phase shift such that the overvoltage on the unfaulted phases remain within reasonable limits. What happens with distributed energy resources is that things become more complicated. Basically, the mechanism driving the overvoltage becomes different. There are two mechanisms under DERs, so it's no longer directly related to shifted neutral. The first mechanism is rejection of power to the unfaulted phases, and the second is what we call load rejection overvoltage. So the rejection to the unfaulted phases is basically the inverter. The main difference is that the inverter acts as a current source. The current of the inverter is regulated by internal controls. So when a phase B to ground happens, the power on phase B drops to 0. So the inverter, in trying to maintain the overall three-phase power, it increases the power on phase A and C by 150%, and that is done by increasing the currents. So because of the increased current, the voltage also increases. So for example, theoretically, this could be 1.22 per unit for 150% power on unfaulted phases. So this is the first mechanism. This is related to the fault. The second is load rejection over voltage, which is not related to the fault. It could happen even without a fault, and it has to do with islanding condition. So assume that we have an inverter-based resource or a DER supplying a local load and being connected to the network. Let's assume that the load is 2 pu impedance, and the inverter is generating 1 pu current. So half of that current goes towards feeding the load, and the other half goes into the grid. And the voltage across the load is 1 pu. When islanding happens, the entire current of the inverter, the 1 pu, has to flow into the load. So the voltage increases to 2 per unit. And basically, this is called load rejection over voltage. And this voltage depends, of course, on the ratio of generation to load. If, let's say, the impedance is 0.5 per unit, if the load requires 2 per unit current, after islanding, the inverter could only supply half of that. So the voltage drops to 0.5 p. So it could be an under voltage condition depending on load to generation ratio. So basically, the mechanisms driving GFOV under DERs are different. The challenge is that the classical methods to analyze GFOV do not apply to inverters. And also because the mechanism is different, it's not, the inverter is not basically directly causing neutral voltage shift. It's not a voltage source. The best mitigation, the classical mitigation option, effective grounding, may not work reliably, and fast inverter trip is the best mitigation option. So essentially, open the inverter as soon as a fault happens or an islanding happens. But that could be expensive. For example, if you use a direct transfer trip signal, communication infrastructure is needed, and basically it's more expensive. So there's a need for low-cost mitigation options. And in terms of simulation requirements, basically the DER model, a sequence domain DER model is sufficient if it is not using the fault ride through mode. because the FRT is not typical of DER inverters. And also, if we use a DER model, for example, a sequence domain model, we need to make sure that inverter terminal voltage under, in no case, it does exceed the nominal voltage substantially. Also, the load models need to be loads need to be modeled properly. One major finding of this study was that motor loads have an impact on overvoltage, so they need to be represented accurately. And also nonlinear effect, if arresters are present and also transformer saturation, they need to be also modeled in detail. So to make sure that these modeling concerns or modeling considerations are met, we use EMTP. So this is a case study that we performed. So basically, this is the system. The subtransmission system was at 70 kV and was supplied by a transmission network. And this is the main breaker. Basically, when there's a ground fault on the subtransmission system, this main breaker opens and the entire downstream network, downstream subtransmission becomes island. And there are 6 feeder locations within this distribution network. And essentially, these feeders, their internal loads and PVs, they form an island. So there are different PV locations. There are some existing PVs and some future PV installations. And a particular thing about this specific subtransmission network was presence of large amounts of motor loads. So this was a region with large agricultural loads, also large motor pumps for irrigation purposes. And that also had to be studied here in the simulation. And also the substation transformers that you see that basically feed each feeder, they all have a arrestor, surge arrestor on their primary side to protect them. So the EMTP model development, basically we received these data from the utility. The subtransmission network data was provided in ASPEN, and we translated that to EMTP. The distribution was modeled in SIME, was provided in SIME, and we also translated that to EMTP model. And additional motor loads were provided, the type of motor, synchronous induction, and horsepower. And we also added complementary typical data to enable EMT simulations. And also arrestor nameplate data was provided. And that includes basically with those nameplate data, we estimated the arrestor energy handling and transient overvoltage withstand capability. And also we generated a generic current voltage curve for EMT simulations. The DER data, including control and onboard protection, was also provided. And we also used the generic EMT-DER model and added complementary data to that. So here is a cross-examination of EMTP to ASPEN. Basically, the EMTP model was able to match the ASPEN model that was provided by utility. You can see the match is almost perfect. And the DER representation, we basically, this is the onboard protection that was provided. This is essentially following the California Rule 21 tariff. And we also studied different DER control modes, power factor versus volt var. And the finding was that these different control modes has a negligible impact on GFOV. And also another key finding was that this onboard protection may not trip during a ground fault over voltage, because the PV terminal voltage only sees marginal effect. There's high side, so it sees a marginal effect by the high side ground fault. And so essentially the conclusion was that we cannot rely on the onboard protection to trip during the ground fault. And motor loads, so it's necessary to adequately represent them. And here is basically why motors contribute to GFOV. Essentially, here is the result. I'm showing the speed of the motors, the different types of motors. They had larger scale synchronous and induction motors, plus small scale commercial motors, 50 HP and 1 horsepower. And basically, when the islanding happens, this is when the islanding happens, the motors speed down gradually, and during until they speed down, they hold up the island. So basically, they are contributing, and this is the voltage the voltage of the island that is held up by motors, essentially. So you can see it lasts for quite some time. And if you're interested in knowing more about this, there was an incident earlier this year in Hydro 1, where an island was exclusively supported by induction motors for a period of essentially infinitely long time until the island was manually cleared. So basically, the motors contribute to GFOV, and they need to be represented in detail. And also, this is the result from one of the synchronous motors in this simulation test. And you can see that before the fault, before the islanding, it was acting as a in the motor mode, but after the islanding, it was acting in generator mode. So essentially, it is so energizing the island. So the conclusion was that if substantial amounts of motor loads exist, they need to be represented in detail. Even with no PVs, motors contribute. And arrestor model, basically, we generated the VI curve. The most important regions, so the arrestor, basically, some background, it acts as a nonlinear resistor. So the objective is to protect the equipment against surges. So at voltages below rated or close to rated, the arrestor acts as essentially an open circuit. But when there's a surge, the arrestor acts as a short circuit. So basically, for switching surges and lightning impulse surges, the arrestor is operating in this region, and for rated voltages in this region. And in between, there is a region, operating region for temporary overvoltage, and the arrestors during ground fault overvoltage operate in this region. Basically, it's a few tenths of amps up to a few hundred amps. So this region needs to be modeled in more granularity for GFOV studies. And basically, we could skip these in the interest of time, but this is the operating region that we represented in more detail. And in this region, basically, if the arrestor conducts, the current is a 60 hertz fundamental frequency, but it's highly polluted. It's highly, the harmonic level is high. And so because of these nonlinearities, basically the arrestor, if there is a small difference in characteristic, it could be a large difference in conductive current, energy consumption of the arrestor. So that's why it's best to consult with arrestor manufacturer for a specific curve data. And also this curve depends on the service experience of the arrestor, the batch in which the arrestor was based. Yeah, essentially, even arrestors of the same model and manufacturers can have different VI curves. And arrestor energy capability, so we had to estimate those because basically these are not provided for, for the type of overvoltage that we see for GFOV type voltages. The arrestor withstand energy capability is not tested or published. So we used the energy handling capability, the published energy handling capability of switching surge, and we estimated the GFO withstand capability using that, and we compared the EMTP results to that estimated energy. And another important thing is that basically regarding the sharing of arrestors. So basically you see here, we have multiple arrestors in parallel in the subtransmission zone. And the question is, can these arresters share the overall energy caused by the overvoltage? And basically the answer is not necessarily. In simulations, because we use the same identical VI curves for all these arresters, we may see good sharing between arresters, but this is not what happens in reality, because there may be a small difference in characteristic VI characteristics because of the different service experience. And that could mean that one arrestor is conducting significantly more current. It's basically one of the arrestor, the most severely impacted arrestor, could take the highest duty, and it is likely to basically, in reality, have more energy consumption than what is shown in simulation. So we cannot basically rely on ideal arrestor sharing in practice. And the temporary overvoltage capability curve, it basically says the duration of the overvoltage that the arrestor can withstand. So there are two duty curves, that the no prior duty and prior. For GFOV study, we use a no prior duty curve. And essentially here in this region, the red one, we are, at this point, for example, we are exceeding that capability. At this point, we are below that capability. So we're good. So we also used this curve. So look at quick look at the EMTP simulation results. So the scenario was there a phase to ground fault close to the main breaker occurring at 5 seconds, and this main breaker opens in 4 cycles, and hence the entire subtransmission becomes islanded. So the islanding happens 4 cycles after the fault, and the DERs continue to energize the island for up to 2 seconds, and then they are tripped. And so basically we're considering the worst case scenario where DER internal protection does not operate until 2 seconds. It could be the islanding detection protection, or over under voltage and over under frequency. So we assume the worst case scenario, and the objective is to see if or when DR penetration presents a GFOV problem. At the existing PV level, the generation to load ratio was 3%, which is quite low, and there was no risk of GFOV based on simulations. But as we increase the level of PV, the voltage level increased, and basically the GFOV risk increased. And another objective, so the first objective was to see at which DR penetration level the GFOV becomes a problem. And then the second objective was to evaluate GFOV mitigation options. And we studied various simulation scenarios. We started from 0 GL ratio, basically with no PVs, and went up to 200% in the GL ratios. And we recorded the overvoltage and also the location of the fault. So the base case has the fault close to the main breaker, but we also moved the fault around the network to see the impact on overvoltage. Arrestor non-sharing, so we had a case where we basically, in simulations, we put all duty on one arrestor and see what happens to the energy of that arrestor to try to capture what is expected to happen in reality with non-sharing of arrestors. Also, DER control mode, as I talked about, volt var versus power factor. So essentially, traditional, the older PVs, the ones that were generated before 2018, they were using constant power factor, but with new rules after 2018, they were using volt var. And we simulated both, and there was no significant impact on GFOV, essentially because the time response of the control was simply too slow to have any significant impact. And location of future PVs. So the utility provided the location for future PVs, but we also, for higher levels of PVs, beyond what they plan to install, we put them on different locations to see the impact, and also the impact of arresters. So this was a sort of a theoretical study. So we removed the arresters and compare the overvoltage to the case where we have the arresters. Basically, in this case, arresters, if they conduct, they act like a load. So they help mitigate the overvoltage essentially. But the objective was to see whether they can sufficiently mitigate the overvoltage, whether they can sufficiently modify the voltage to keep it below, to keep the voltage level within reasonable limits. The objective and the conclusion was that no, basically the arresters, although they clamp the overvoltage by acting as a load and conducting current, however, their energy rating, estimated rating may be exceeded, and they are likely to be destroyed in that process. And we're basically, in making these conclusions, we're looking at the high side voltage of the transformers, basically on the subtransmission network, and also the energy dissipation of the arresters. And here's a summary of the conclusions. So at different GL ratios, so basically we are increasing the PV integration level from 0% when there is no PV up to 200%. And we are looking at peak phase to ground. So you see at 0%, it was 1.45 PU, and at 200%, we went up to 1.90 PU. And this is a summary of key findings. Basically, at 0%, with no PVs, we had a base 1.45 PU overvoltage. And the reason for this is basically because of the motor loads. Essentially, some of them, they operate in the generator mode after islanding, and that leads to an overvoltage. However, this overvoltage was not large enough to cause the arrestor to conduct a sufficient current to modify the voltage. So the conclusion was that the utility does have an existing OV condition, but it's not, I mean, they cannot see the impact necessarily because it's just tickling the arresters in a sense. And this condition with 0% GL, it's not, it can happen, for example, during the night because these motors are running 24/7. So during the night when there is no PV, basically this overvoltage condition can happen, or it could be even worse than this number because the loads, for example, in pre-dawn hours where the loads are lower, this overvoltage can increase. With existing level of PV at 3%, there was no significant change in overvoltage because basically the PVs are very low. And so this overvoltage at the existing level of PV is mainly characterized by motor loads. And again, in this case, the arresters did not conduct sufficient current to modify the voltage. And we increased to 21% with 6 megawatts of PV for future PV installations, basically. And it increased the overvoltage a little bit, but still we didn't see significant conduction by arresters. The level at which the problem started to occur was 67%, and the overvoltage increased to 1.82. So the arresters started to conduct heavily, and they clamped the overvoltage, but their energy rating exceeded the estimated arrestor energy capability, and therefore the conclusion is that at this voltage, the arresters are likely to be destroyed. So another interesting thing is that this level that we captured here, it was basically the GL level at which the GFOV problem started to occur. So at higher levels, 100%, 150, and 200, this voltage increases and the problem it also exists there. But the interesting thing was that this number was exactly matching the number that the utility had currently as their hosting capacity cap. So they were impressed that EMTP was able to capture this exact number. And it shows that basically with all the modeling details, if they are sufficiently accurately represented, we can have a reasonably good accuracy. And here is sample simulation results. So before the islanding event is at 5.04, and the fault is at 5 seconds. And basically before the islanding, this is the voltage on the high side of the transformer. The voltage was 1 PU, but after islanding, the voltage increased to 1.82 PU. This is the result of the GL 67%. and it shows basically that the increased voltage on the high side of the transformer is sufficiently large to be detected by transformer protection. For example, if we properly set the transformer 59P phase over voltage protection, then it could trip on this overvoltage, and this could be a mitigation for overvoltage. For example, in one of the tests, we used 59P with 1.4 pu pickup voltage and a 5-cycle clearing time. And basically, as soon as the overvoltage happened, very shortly after the transformer protection tripped, and it isolated the MV feeder behind the transformer. So this could be a GFOV mitigation. This was actually one of the effective options that we studied. And this is the voltage on the low side of the substation transformer. So as you can see, before the fault and after before the fault and islanding and after, the voltage remains close to 1 pu. And this is because of the grounding connection on the low side of the substation transformer. And what it means is that on the low side, the DERs, because they are on the low side, they may not see an overvoltage. So the voltage remains close to 1 pu, even though on the high side it's very high. So because it doesn't see an overvoltage, the DR protection may not trip. So the conclusion here was that we cannot rely upon DR protection to detect and trip on overvoltage. And this is the V0 voltage of the transformer, the neutral point voltage, basically. So before the fault, it was, we're assuming a fairly balanced network, so it's 0. After, it increased to 1.15. So it also means that properly set 3V0 protection can detect GFOV. Basically, in this case, the overvoltage was 1.15 PV. So if the pickup setting is set below this, the transformer protection is able to catch the GFO condition. And here is a look at the speed of the motors. So the objective here is to show you that because after islanding, the frequency of the network is characterized by the speed of motors. So you can see that the frequency basically declines gradually and slowly, and that means that the DER frequency protection may respond slowly. So our study suggested that the fastest acting protection was the transformer 59P. And so both for PVs, the overvoltage protection and the frequency protection did not act fast enough. And this is the arrestor current. So you can see before the fault, the arresters before islanding, the arresters were not conducting, but afterwards, because of the high voltage, and they started to conduct heavily. And this is a look at their energy consumption, and comparing it to energy rating. You can see that for some arresters, the energy rating is exceeded. So this also indicates that if we monitor the arrestor currents, that could be used as an indication of ground fault over voltage. And this is one of the mitigation options, basically, to analyze the arrestor current and basically issue a trip signal upon detection of high currents. And GFOV mitigation options. So basically, we studied 4 options. Transformer 59P that I talked about, the conclusion was that it is effective, and it isolates the NV feeder quickly, and therefore it basically prevents arresters to exceed their energy rating capability. And also, the one note here is that when the NV feeder is isolated, there could be DERs and loads within that feeder, within that isolated feeder. So we could have a pocket with load rejection over voltage. So there could be an overvoltage in that isolated pocket. So for that reason, if future DERs are certified to IEEE 1547 2018, that is expected to limit the duration of load rejection over voltage. The other mitigation option was DR onboard protection, and the conclusion was that it cannot be relied upon. And another option was to double the arresters to see if by doubling them they could still remain within their rated energy consumption capability. And the conclusion was that basically because of the arrestor non-sharing, because of the differences in VI curves, the doubling the arrestors may not help. So they may not match each other if they're not, if they don't have the same experience, service experience, then yeah, even with the same manufacturers, we may not have arrestor sharing. So still one arrestor could take most of the duty. And arrestor sensing, basically, simulation suggested that this option is also possible by looking at the current and analyzing the current of the arrestors. So pros and cons of this method depends on system configuration and need to be consulted with the utility. And this is a look at the results. So basically, we are showing that the transformer 59 protection is the fastest to operate in simulated scenarios. And after that, after the feeder is isolated, the onboard PV protection operates basically either overvoltage or frequency protection. And arrestor energy also remained within capability, and also the temporary overvoltage capability of the arrestor was satisfied. So basically, with the transformer 59 protection, the transformer was exposed, the arrestor was exposed to the overvoltage for a short amount of time. So we are well within the capability of the arrestor. And here are the key takeaways. Basically, the first conclusion was that the presence of large amount of motor loads creates a GFOV concern without any DER feeding the fault. Also, in terms of mitigation, the properly set substation transformer phase to ground phase overvoltage protection is an effective mitigation of GFOV, and also DERs that have onboard protection based on this, the IEEE 1547 may not detect the overvoltage and cannot be relied upon to trip during transmission ground faults. And also EMT simulations can accurately capture and represent practical considerations and more complex mechanisms associated with GFOV under DERs. So yeah, that's it. Thanks for your attention, and let me know if you have any questions.
Thanks, Aboutaleb, for a very good and I would say in-depth presentation. We do have a few questions, so let's start with this one. Related to the overvoltage levels that can be reached with the distributed generation during a ground fault. You mentioned that there are situations where we can go beyond 1.7 per unit, right?
Yeah, depending on GL ratio.
Right, right. Can you explain a little bit the mechanism of how this, how we extend beyond 1.7 per unit? And also, if you could give us a little bit more detail on that, on what you explained right there about the overvoltage mechanisms with inverters in the way they're different from traditional generation. You mentioned that all of a sudden the inverter would try to push 1.5 per unit power in the healthy phases. So is this an inherent feature of traditional inverter control architectures, or can you explain this power reference in healthy phases a little bit?
Yeah. So basically, the overvoltage in terms of so in response to the first question, the mechanism is a combination of these two phenomena: the rejection of power to unfaulted and load rejection overvoltage. So both factors contribute to overvoltage under the ERs. So as to why load to generation ratio has an impact, so it's basically because the inverter is regulating the current. So after islanding, depending on the load, the required load current, the voltage across the load could increase or decrease. So the level of this voltage depends on generation to load ratio. So this example that I'm giving here, it's It's a theoretical example. It's just for illustration purposes. You see, for example, in this case, the voltage increased up to 2 pu because the impedance was 2 pu. If that means that the generation to load ratio here is 2. If I increase that, the voltage here also increases. So that's the response to the first question, why we see such high overvoltages under inverter-based resources at high integration levels, because basically these two mechanisms, they both contribute to the voltage. Whereas with synchronous generators, theoretically, the voltage could go as high as 1.73 per unit. And this is when you have light loading. If you have heavier loading, this voltage will decrease. Basically, the heavy load will have some mitigating effect. Now, the other question as to why the power is rejected to unfaulted phases, it's, as you mentioned, it's because of the way inverter controls are designed. Basically, so what happens is when the voltage when the power becomes zero on the faulted phase, now the inverter control is designed to provide to follow the commanded active power set point. So before the fault, the command is 1 pu, and after the fault, the inverter tries to re-regulate the currents such that the overall three-phase power remains close to that 1 per unit. So for that, because the voltage on the power on the faulted phase is dropped to 0, the inverter control needs to increase the power on the unfaulted phases by 50% each. Okay, and that is done by re-regulating the currents. I mean, it's common for inverter control to regulate positive sequence current. So essentially, inverter delivers a set of approximately balanced three-phase currents. The amplitude of the current is increased until the power reaches 150%. So that's the mechanism. But keep in mind that the inverter currents are subject to limits. So if the inverter current hits a limit, for example, typically 1.1 per unit limit, the inverter may not be able to supply this active power, or may not be able to increase the active power up to 150%. And so this number assumes that the inverter has enough headroom. But if the inverter doesn't have enough headroom, this may be lower, and this number 1.22 per unit may also be different.
Right, makes sense. You mentioned that you have been using generic EMTP PV models from the renewable energy toolbox.
Yeah.
You have done no modifications to those models, or if you did modify something, what was it?
Yeah, so the main modification was addition of the onboard protection based on California Rule 21. The existing library model did not include this, and we basically manually implemented it and added it to the model. So it was nice that we could see inside the model, and we could add or modify the existing components to match what the utility provided.
Right. Sounds good. So it was a sort of a minimal change. Let's see, what else could we ask you? When it comes to the measurements on the high voltage side of that substation subtransmission transformer, we have a question on whether it may prove to be too expensive to measure that voltage.
Yeah, it's true. Basically, if you're talking about the implementation of 59P protection, you need to have PTs on the high side of the transformer, and yes, PTs could increase the cost of that mitigation options. You're right, but compared to so in some cases there already exist PTs on the high side, so you don't need to add PTs on those cases. But if they don't exist, then yeah, there's an increased cost associated with that. But basically, comparing that, so this mitigation option depends on, it may change from utility to utility depending on their system configuration and existing equipment and measurement equipment. So what we are assuming is basically that the substation transformer does have existing PT.
Right. Okay, let's go with one more, and this may be a complicated one to answer, but it's up to you. I mean, how do you differentiate between ground fault overvoltages and load rejection overvoltages when, in many cases, they happen at the same time? Did you have to separate them in your analysis in some way?
No, it's basically the overvoltage is a combination of the two.
Right.
So that's what we considered also. So what you see here, it's basically both related to the ground fault, also to the island load rejection overvoltage. We did not quantify the impact of each.
Okay. Well, let me see. Yeah, what are your thoughts about the grounding transformers as a solution for GFOV?
Well, yeah. So as I mentioned, it's in traditional systems that is the widely accepted solution.
Yeah.
There are practices to define effective grounding, the impedance ratios. So that is well established for traditional systems. With inverters, there is still debate going on as to basically what is an effective grounding when you have inverter-based DERs. And so the best solution, the grounding transformer may not work reliably because the GFOV issue is not exclusively related to zero sequence. So the best solution, as I mentioned, is to trip the inverter as soon as possible.
Right. Well, I think these are all the questions we had for you, Aboutaleb, today. Thank you very much for your presentation. Thank you for all this material. It was a lot. I could tell that you struggled to finish in 45 minutes. So thank you for that, and we'll look forward to hopefully having you next year again.